Congruent and similar figures can also appear in a coordinate plane. Remember, translations, reflections, and rotations preserve the image, size, and shape for all figures involved, and this makes the figures congruent. Dilations, on the other hand, preserve only the shape of the image, but it changes the size of the image, and that makes the figures similar. Determine if the two figures shown are congruent, similar, or neither. The pre-image is dotted, and the image is solid. Then, explain how one figure was obtained from the other through a series of translations, rotations, reflections, and/or dilations. So let's actually start by looking at both of these. They generally have the same shape. We have two right angles in the bottom. We have two obtuse angles here, and we have, it looks to be obtuse, where the other two sides come together. And it goes from being 1, 2, 3, 4 units long for that side to being 2. So this appears to have a dilation involved, making the figures similar. And now we've got to explain how we get from the dotted to the solid. Let's start by drawing in some lines here into the origin so that we can see what exactly is happening. So if we go into there, because when figures are dilated, they will follow the straight lines to the origin in order to get the new figures. So if we follow this, again, this was 1, 2, 3, 4 units. We want it to go down to 2 units. So if we actually see between here and here, this is 2 units. So that's going to be one of the new sides of our shape. And then this is 1, 2, 3, 4, 5, 6 down. So this will be 3 down. 1, 2, 3. And notice it falls right here on one of those points. And then it goes out 2 again, right here. And then this is down 3 to the right 2, I'm sorry, to the left 2. So instead of down 3, we're going to go down 1.5 and over 1. So this is going to be where our middle figure, or the dilation figure, that's happening. So we have a dilation about the origin. With a scale factor of 1/2. We made it half of the size. And now let's actually look at what the relationship is between our purple figure that we just drew and our navy blue figure on the other side. So now we have from -2, 4, we went to 2, 4. -2, 1 to 2, 1. -4, 4 to 4, 4. This appears to be a reflection across the y-axis. Across the y-axis. So here is our explanation. We had a dilation about the origin with a scale factor of 1/2, followed by a reflection across the y-axis. And the solutions that are showing on this slide verify that our solution found when executing this example are indeed correct. Determine if these two figures are congruent, similar, or neither. We found that the original black dotted pre-image was similar to the navy blue solid image. And explain how we got from our original figure to our image. Well, we dilated our original figure about the origin with a scale factor of 1/2, and then we reflected the smaller one across the y-axis. If you were to do it in symbolic notation, that would be from xy to 1/2 x, 1/2 y, to the negative of our second xy coordinates. If you were to write it all just in terms of xy, you would write it as xy goes to 1/2 x, 1/2 y, which then goes to negative 1/2 x, 1/2 y. Determine if the two figures are congruent, similar, or neither. The pre-image is dotted and the image is solid. Then explain how one figure was obtained from the other through a series of translations, rotations, reflections, and/or dilations. Okay, so first let's look at our two figures that we have. We have this trapezoid whose top is 1, 2, 3 units long, and the bottom is 1, 2, 3, 4, 5 units long. Okay, so this top corresponds over here, 1, 2, 3, and then we have 1, 2, 3, 4, 5. Okay, so all of these measurements are staying the same. So therefore, our two figures are congruent. And now we have to explain how we got from this dotted figure to the solid figure. Well, because it's going from having the base as the bottom, or the longest base at the bottom, to the longest base over here being to the left, I know it's going to rotate 90 degrees. Let's try to translate it so that this corner right here, that's going to actually match this one. So let's see how many we have to translate to the right to get from this point to this point. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if I translate everything, 9 units to the right, that will put our trapezoid at this point, and then from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, this point. 1, 2, 3, 4, 5, 6, 7, 8, 9, that'll be here. And this one, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here is going to be the middle image diagram that we have here. So we could translate it 9 units to the right, and then we have to rotate it 90 degrees clockwise this direction. Because this point right here stays in the same position, we're going to rotate it about that one. If we rotate it about the origin, it'll end up being way over here. So we're rotating it about the point 1, 2. And when we do that, we will indeed get our final image value or figure. So here we can see that the solution that we came up with of translating the the trapezoid 9 units to the right first, and then rotating it 90 degrees clockwise about the point 1, 2, does indeed give us our image figure. This isn't the only correct answer, though. Try to take a moment and pause this video to see if you can find another way to move the pre-image to the image. Another alternative that could have been used was a 90-degree clockwise rotation about the origin. And if we do that, it matches up with all of the points in the orange orange trapezoid. And then once we get this middle step right here, we could go to the left 1 unit and down 6 units, and it will give us our final value. So another solution was to rotate the figure 90 degrees clockwise about the origin, and then translate it to the left 1 and down 6. Left 1, down 6, left 1, down 6, left 1, down 6. As a formula, that would be xy to y negative x, followed by y minus 1 to negative x minus 6, if you were to write it in symbolic notation. Notice there's another or here. There is yet another way that you can move the original pre-image to the image point. If you'd like to think about how that could occur, pause the video and try to see if you can figure it out. So yet another way to get from this original pre-image to this image would be to reflect the trapezoid across the line y equals x, and then to translate it to the left 1 unit and up 5. To the left 1, up 5, left up 5, left up 5. And we can verify that xy goes to yx, which then goes to y minus 1, x plus 5. And we're going to verify that with points. So here we're starting off at -3, 2. And this point here is -8, 2. So first we would switch the x and y coordinates around. So 2, -3, that does work. 2, -3 corresponds to this one. And then 2, -8 corresponds to this one down low. And then we are going to the left 1, so we're doing 2 minus 1, which is 1, and -3 plus 5 gives us 2. That does correspond to this point, 1, 2. And then this point here at -8, 2 goes to 2, -8. And then if we subtract 1 from 2, we get 1. And if we add 5 to -8, we get -3. And that does correspond to this point here, 1, -3. So this is the third way that you could figure out the transformations that were used to get from the pre-image to the image. Determine if the two figures are congruent, similar, or neither. The pre-image is dotted, the image is solid. Explain how one figure was obtained from the other through a series of translations, rotations, reflections, and/or dilations. Well, let's examine these. So the pre-image is dotted, so we're starting with the smaller one down here. And its top and bottom have lengths of 1, 2, 3, 4. Okay, so in the pre-image, the bases have a length of 4. And in the image, the bases are 1, 2, 3, 4, 5, 6, 7, 8. In the image, the bases are 8 units long. Okay, so we usually set up a ratio as image over pre-image, and that equals 2. So 8 divided by 4 is 2. This is the scale factor. So we have similar figures. And we have a dilation going on. So we are dilating with a scale factor of 2 about the origin. So that is one middle step that we have here. So let's actually draw our new parallelogram in there that is not showing for the middle step. And to make this a little bit easier, we're going to write down the original coordinates of our pre-image. So we have 3, -1. We have 7, -1. We have 2, -3. And we have 6, -3. And if we multiply these by 2, because of that scale factor of 2, coordinates will become 6, -2, 14, -2, 4, -6, and 12, -6. So let's plot these points. So we'll have 6, -2 right here. We have 14, so here's 10, 11, 12, 13, 14, -2, so it's kind of going to go over this 3. 4, -6, right here, and we're at 12, -6, so that's going to be right about here, over top of that parenthesis. So if we connect these to make our parallelogram, it'll look something like this. Okay, so this is the missing step that we have showing now. And next we have to determine how much we need to translate or move this red parallelogram to get the blue one. So if I take this corner right here, its corresponding corner is this one up here. So let's see how many we have to go. We have to go 1, 2, 3, 4, 5, and to the left, and up 1, 2, 3, 4, 5, 6, 7. So then we're translating left 5 and up 7. And we can verify that with this one too. So left 5, 1, 2, 3, 4, 5, up 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yep. So these are our final answers for this question. And this slide verifies what we just found, that these two original diagrams are similar, and the transformations that are happening are a dilation with a scale factor of 2 to get us this green parallelogram, and then we would translate this green parallelogram to the left 5 units and up 7 units. If we were to write this as a formula, it would be xy to 2xy, showing this, to the second x coordinate minus 5, the second y coordinate plus 7, and if you substitute the 2x and 2y in for those, you would get this final formula.